Hello, today probably the concluding lecture of my course on power electronics. I will try to cover AC voltage regulators. Input is AC, output is also AC. Frequency of input and output is the same, only the magnitude of output voltage is varied. Okay, see here, we are here, input is AC, output is also AC, frequency constant, variable voltage. They are known as AC voltage regulators. AC voltage regulators. Okay. Where are they used? They are very popular in fan regulators, light intensity controllers. I had told you that if the induction machine is driving a fan type of load, the speed can be varied over a wide range by varying the magnitude of the input voltage, frequency being the same. Okay. The type of load is fan type of load, wherein TL is proportional to omega square. What is another advantage? It is possible to operate the machine at maximum efficiency over a wide range. How is that possible? Just see here. We all know that output is equal to input minus losses. Now what are the losses? There are two types. One is constant loss plus the variable loss. Constant losses, I will name them as core loss. Okay. They depend on flux. Frequency remains constant here, so it depends on flux. Flux in the machine remains constant if V by F or E by F is held constant. That we had seen while doing inverters. So if flux remains constant, core loss in the machine, they remain constant. So when does the efficiency of the motor is equal to the maximum efficiency? It is when the constant loss is equal to the variable loss. The variable loss depend on load. Okay. Basically they are I square R losses. Okay. Now if the load on the machine comes down, I square R losses also come down. So how do I operate the machine at neta is equal to neta max? What do I need to do is, as the load comes down, you reduce the flux such that motor operates at maximum efficiency. You have to reduce the flux such a way that constant losses are equal to the variable losses. So in principle, using the phase regulators or AC voltage regulator, it is possible to maximize the efficiency at light loads. If I keep the frequency constant and try to reduce the voltage, we had seen that flux in the machine comes down, it reduces. Therefore, core losses reduces. Okay. Variable losses is a function of load. Since the load is reducing, I square R losses, they come down. Efficiency is maximum when core loss is equal to the variable loss. So in principle, it is possible to maximize the efficiency at loads. Why am I saying in principle? The reason I will tell you sometime later. Okay. So case 1, load is purely resistive. Okay. Input is single phase AC. I have used two SCRs, T1 and T2. They are connected anti-parallel. Okay. Now you can replace this combination by a track, the device which is used in fan regulators. I had shown the fan regulator, also the device, during my introductory lectures. Okay. So load is purely resistive. Okay. So this is the input voltage, this sinusoidal. In the positive of T1 is triggered at alpha. Okay. Gate pulse to thyristor 1, and in the negative half cycle T2 is triggered at an angle alpha. Okay. When T1 is triggered, input voltage Vs is equal to output voltage. Okay. Load is purely resistive. Current and voltage are in phase. Okay. So the waveform of source current, which is equal to the load current, is same as V0 itself. Okay. So input voltage becomes 0 at omega t is equal to pi. At that instant even V0 becomes 0, Is also becomes 0, the load current also will become 0. I am assuming the device is ideal. Okay. So from omega t is equal to pi plus alpha, there is no current flowing in the circuit. Okay. Load is purely resistive, that is the reason. And again at pi plus alpha, T2 is triggered. Okay. A negative voltage is applied to the load. Okay. So what is the limitation of this sort of a control? Harmonic content is high. Is an odd function, source current as well as the load current, they have all odd harmonics, and they give rise to heating in the load. Okay. And the source side, they affect the voltage at the point of common coupling. I had told you that effect of harmonics I had discussed during my converters lecture. If there are harmonics in the line, due to the finite impedance of the line, voltage at the common point of coupling, it gets affected. Okay. Now we will take the second case, load is RL. Okay. Things are not as straightforward as when the load is purely resistive. T1 is triggered at alpha, and again T2 is triggered at pi plus alpha. And I am making another assumption. Assume that IL, that is equal to the source current, becomes 0 before the SCR is triggered. Okay. I will repeat, the assumption is IL becomes 0 before the SCR is triggered. So load is passive, at alpha T1 is triggered. Okay. So when T1 starts conducting, input voltage is same as the load voltage. Okay. So voltage is applied to a RL load. Now it is, the circuit equation is R into I plus L di by dt is equal to Vm sin omega t. Okay. See, I will show you the equations. This is the equation. The solution looks like this, or solution can be given by this equation. Vm by Z sine omega t minus phi plus a into e to the power minus t by tau. We had derived this equation in the very first lecture in converters, where z is equal to square root of r squared plus omega l squared. Phi is tan inverse omega l by r and tau is l by r. So how do I determine the value of a? The boundary condition is I is equal to 0 at omega t is equal to alpha. I told you that current becomes 0 much before the thyristor is triggered. Substituting or using this condition, I can solve the equation. I will get the expression for current. It is given by this equation. Vm by z into sine omega t minus phi minus sine alpha minus phi into e to the power r by l into alpha by omega minus t. So this is the equation for current. So there is a sinusoidal component and a decaying component. Okay, so the current waveform looks something like this. It starts from 0, it ends a peak somewhere in between pi by 2 to pi. It attains a peak when instantaneous value of the input voltage is equal to R into I. When I is equal to I max, L di by dt is 0. So at that time Vi should be equal to I max into R. Somewhere here it attains a max. It reduces and it becomes 0 somewhere after pi. Until the current is flowing in the circuit, input voltage is equal to the output voltage. Okay. So at beta, current becomes 0. And till another thyristor is triggered, that is T2 is triggered at pi plus alpha, there is no current flowing in the circuit. There is no current flowing in the circuit. Say from beta to alpha or pi plus alpha, there is no current, and therefore there is no voltage. And at pi plus alpha, you trigger T2, and whatever that happened in the positive half will happen in the negative half. Actually, this should continue beyond beta here. Say current becomes 0. That I have shown you. I have shown this waveform here. Okay. Actually, this part should come here. So whatever that happened from pi to beta will happen from 2 pi to beta. Okay. Now, so this is the equation. Assume that at omega t is equal to beta, I will again become 0. Okay. So you substitute this condition in the previous equation. Okay. So what do I get? You will get sine beta minus phi is equal to sine alpha minus phi in this term. Now, if alpha is equal to phi, in other words, if the trigger angle is same as the power factor angle, what does the equation 1 say? It says that this term will become 0. Okay. So you have the current which is given by Vm by Z into sine omega t minus phi. Current is sinusoidal. Current is sinusoidal, lags the input voltage by an angle phi, which is given, which is equal to the impedance angle. Okay. So if trigger angle alpha is equal to the power factor angle, current is sinusoidal, lags the input voltage by an angle phi, which is equal to the power factor angle. How does the voltage and current look like? See here. Trigger angle alpha is equal to phi. Current is sinusoidal. Okay. Now current is sinusoidal. That means either it has to flow through either T1 or T2. So you will have the input voltage is same as the output voltage. The output load applied voltage to the load is sinusoidal and is equal to the input voltage Vi itself. Therefore, VO is equal to Vs is equal to Vm sin omega t. There is no control over the output voltage. Whatever is there at the input is appears at the output. Current is sinusoidal, lags the voltage by an angle phi, because SCR is triggered at an angle alpha which is equal to phi. The previous case we saw alpha current was discontinuous. Current was discontinuous. It can happen only when alpha is greater than the power factor angle. I will repeat, current is discontinuous when alpha is greater than the power factor angle. Okay, so this is the condition. When alpha is equal to phi, IL is equal to IS, it is discontinuous. And V naught is equal to Vi. At this instant T1 is triggered, it continues to conduct till pi plus alpha. At that instant current becomes 0. So T1 turns off, immediately T2 is triggered. So it goes on. Okay. So output voltage cannot be controlled, or in other words, output voltage is equal to the input voltage. Whereas if alpha greater than phi, IL is discontinuous. So current becomes 0 here, and thyristor may be triggered somewhere here, current starts increasing. So during this period you will not have any current. So during this duration T1 is conducting, and the conduction period for each device is pi radians. So we have seen in a AC voltage regulator, you can control the output voltage if the trigger angle alpha is greater than the power factor angle. Current is discontinuous. Current is discontinuous and it is sinusoidal if the trigger angle alpha is equal to the power factor angle. Output voltage is equal to input voltage. There is no control over the output voltage. Conduction period for each thyristor is pi radians. Now what happens if alpha is less than phi? Okay. If alpha is less than phi, V naught and IL do not vary with alpha. In the positive off, you might have triggered T1 at alpha, and alpha is less than the power factor angle. Current is negative and cuts the 0 axis at phi. Okay. So even if you have triggered T1, it will not carry the current, or current will not flow through it, because current is negative. See here, current is negative only when it cuts the the x-axis, this current starts flowing through T1, and this instant is fixed by the power factor angle phi. Okay. So till phi current is negative, so even if you try to trigger T1, it will not carry the current. It will not carry the current. This current is being carried by T2. So if there is just a sharp pulse, as I shown here, and if your trigger angle alpha is less than the power factor angle, there may not be any current, because there is only one sharp pulse, current is negative, it is flowing through T2, it has to become 0, and that instant is fixed by the power factor angle. Okay. We know that in SCR gate signal should be present till the current through it is higher than the latching current. There is only one pulse, and that has come much before current becoming 0, and then it has to become positive. So there may not be any current, or T1 may not go into conduction. So you need to have a series of large number of pulses till omega t is equal to phi. In other words, till omega t is equal to phi, you should have, or there should be, trigger pulses. Only then you will have a sinusoidal current and a sinusoidal voltage applied to the load. So even if you trigger at alpha, which is less than the power factor angle, changeover from one device to another device will take place only at omega t is equal to phi. Okay. To achieve that, you need to have a series of pulses. There should be a gate pulse present at omega t is equal to phi, a theoretical limit. Of course, it is always preferred to have pulses beyond omega t is equal to phi. Okay. So there is a control over the output voltage for alpha greater than phi. For alpha equal to phi and alpha less than phi, there is no control over the output voltage. Both voltage and current, they are sinusoidal. Current lags the voltage by an angle phi. Okay. So that is about the single phase AC voltage regulators, the principle that is used to control the speed of a ceiling fan or light intensity controller. Now how about controlling the speed of a three-phase induction machine or a three-phase load? What are the possible circuit configurations? I'll show you. There are various configurations, numerous. I'll just show you very few of them. Okay. There are 3 banks here. See, numbering is the same as what we did in 3-phase AC to DC converters, 3-phase bridge, T1, T4, T3, T6, T5, T2, or say T1, 3, 5, 4, 6, 2. Okay. And load is star connected, and the neutral wire, the star point is connected to the neutral. I told you that in single phase, load current, which is equal to the source current, is an odd function. There are all odd harmonics. Okay. How about in 3-phase? We know that 3-phase 4-wire system, the current that is flowing in the neutral wire is minus of IA plus IB plus IC. Okay. So all the triplet harmonics or third harmonic currents will flow through this wire. Okay. Because the fundamental component, that is IA sin omega t minus 120, sin omega t minus 240, the sum of these components, the fundamental component will be 0. Okay. Whereas third harmonic component, they will add up and they will flow through this line, because sin 3 omega t, here sin 3 into omega t minus 120, that is 360, that is equal to sin 3 omega t itself, and same here. So all triplet harmonics will flow through this. So you will have triplet harmonics in the line current. Okay. So the voltage rating of each thyristor is the phase voltage, and current rating is the line current that is flowing. Okay. Because it is a 3-phase 4-wire system, you will have a third harmonic current here. Now when the load is connected in delta, so this could be one of the configurations. Okay. Again, back to back 3 banks, these are 3 loads. Okay. They are connected in each phase. What happens here? The current through the SCR is the phase current. Okay. But then the voltage is the line to line voltage. Okay. But then you will not have third harmonic current in the line. That line. In the previous case, because there is a neutral, you will have third harmonic currents in the line. But in a 3-phase 3-wire system, there are no triplet harmonics. Okay. So this is another configuration. Another 3 banks connecting feeding a star connected load, isolated neutral. Okay. Now there are no triplet harmonics here, no triplet harmonics, because if I apply KCL at this point, IA plus IB plus IC should be equal to it should be 0. Now we found that third harmonic component sin 3 omega t, this also will be sin 3 omega t itself, because 3 multiplied by 120 is 360, that is again 0. This is also sin 3 omega t. So they are in phase, they add up here. So KCL fails. So therefore you will not have triplet harmonics in this case. So there will be triplet harmonics if there is a 4th wire. Okay. Now same as before, we have connected this bank outside, not in series with the load. There are various possible configurations. Okay. We will analyze one of them, a 3-phase AC regulator feeding a star connected load. Let me tell you one thing, analysis of 3-phase AC voltage regulator is bit difficult compared to a 3-phase AC to DC converter. Okay. So that is the reason I will use a resistive load. I will not analyze the circuit for a RL load. Okay. So this is the possible configuration. AN, BN, CN are the phase voltages. Okay. A three-phase resistive load star connected, and you have three pairs of back-to-back connected SCRs. Okay. In this circuit, for the current to flow in the load, two thyristors, at least two thyristors in two different phases should be on. So if T1 is on, current can flow through T6 or T2. Okay. So this is the condition for the line current to flow. Two thyristors in at least two lines must be conducting. Okay. Now for the analysis, I will take the line voltages as the reference. Okay. So I will take VAB as root 2 V sin omega t, BC is lagging AB by 120 degrees and CA by 240 degrees. Okay. Now let's see. Now what is the reference point for alpha, or where do I start measuring alpha from? What did you do in three-phase AC to DC rectification? We took the point of natural commutation as the reference point. Okay. Now here the reference point is taken as, I'll show you, see here it is mentioned, alpha is the delay by phase control in relation to the natural operation that would occur without switches in circuit and source supplying a purely resistive load. Okay. It is like this. What this sentence means is, I have a three-phase voltages, load is purely resistive, alpha is the instant where IA cuts the x-axis or a zero axis and becomes positive. That is the reference point. Okay. I'll repeat. So reference point for alpha is when in this circuit IA becomes 0 and becomes positive, goes positive. So when does this occur? I have defined VAB line to line voltage as root 2V sin omega t. So we know that phase voltage lags the line voltage by 30 degrees. So it is like this. So VIN is given by this equation, minus pi by 6. So in the vector diagram, if I draw, VAB is here, VIN is lags by 30 degrees. And this current is in phase with the phase voltage. So IA. So reference point for alpha is 30 degrees from the zero crossing of the line to line voltage VAB. I'll repeat. Reference point for alpha is 30 degrees from the zero crossing of the line to line voltage. Okay. Now I'll show you. See here, alpha is 0 when positive zero crossing of IA takes place. That is omega t is equal to pi by 6. So therefore, for any value of alpha, it is this omega t minus pi by 6. Okay. Now another condition, we all know that a 3-phase supply is being applied to a 3-phase load. Voltages have to be balanced. So the gating signals for the thyristors in 3 branches must have the same sequence and the phase displacement as the source voltages. See here, gating signals of the thyristors in 3 branches must have the same sequence and phase displacement as the source voltage. Okay. What does it mean? It is this. If alpha for T1, so T3 is connected to B phase, so alpha plus 2 pi by 3, and T5 is alpha plus 4 pi by 3, and T4 is anti-parallel with T1, it is pi plus alpha. For T6, this angle plus pi, and T2, this angle plus pi. So these are the angles. So T1 is triggered at alpha, T2 is triggered at alpha plus pi by 3, 60 degrees, T3 is triggered at alpha plus 2 pi by 3, 120 degrees, T4 alpha plus 5, T5 alpha plus 4 pi by 3, okay, because pi plus alpha plus 60 degrees, it is this, and so on. Now coming to the number of devices conducting at a time. Things were straightforward in AC to DC conversion with 0 source inductance. Okay. That means there is no overlap, commutation overlap period. At any given time, 2 devices were conducting. Things are not very straightforward in AC voltage regulators. I will just show you 2 different cases. Alpha is 90 and another cases alpha is 30. Okay. For alpha is equal to 90 degrees, see I have drawn the line to line voltages VAB, VBC and VCA. Alpha is 90 degrees. Okay. Reference point for alpha is this point, wherein this point is 30 degrees from VAB, pi by 6. So this is the reference point. From here, 90 degrees, wherein you will trigger T1. Okay. So if this is 30, 60, 90. Okay. At this point, T1 is triggered. Okay. I will not tell you the width of the pulse at the gate right now, maybe sometime later I will tell you. After 60 degrees, T2 is triggered. Okay. And again after 60 degrees, T3 is triggered. And again at 60 degrees, T4 is triggered. And again at 60 degrees, T5 is triggered. And this T5, this is 2 pi, just see here. This is this waveform has completed one cycle. Okay, so VAB has completed one cycle. At that instant, T5 is getting triggered. Okay. So this point is same as this. Okay. And after 60 degrees from here, T6 will get triggered. Okay. Now, since the width of the gate pulse could be anything, so I have drawn even T4 here. So it has started from here, it's 2 pi, I can continue in this direction. So instead of continuing in this direction, I have drawn it here. Now, if you see at the 0 crossing omega t, T4 and T5 are gated, or there a trigger pulse exists for T4 and T5. Okay. And VCA is positive. VCA is positive. 4 and 5 there are trigger pulses. Can they conduct? Let us see the equivalent circuit. At omega t is equal to 0, VCA is positive. Gate pulses for T4 and T5 is present. Okay. Now VCA is positive. 5 connected in this manner, 4 is connected in this manner. Resistive load, current can flow. Current can flow in this direction because VCA is positive. Nothing happens in B phase because 6 that is connected. See here, nothing happens in B phase here. 6 that is connected gets trigger pulse after some time. Okay. So only 2 phases are conducting, only 2 phases. And what is the equation for current? IC is equal to minus IA, IC is equal to minus IA. It is given by VCA divided by 2R. 2 circuits are in series, I am neglecting the drop. So VCA is this waveform, magnitude of current is divided by 2R. So it is almost the same waveform, magnitude could be different, that is all. Same waveform as VCA, current IC and IA. IA is negative but IC is positive. Now what happens at omega t is equal to pi by 3? At omega t is equal to pi by 3, VCA is 0 and becomes negative. That means potential of A is higher than potential of C. Resistive circuit, current cannot flow in this direction. So at this point T4 turns off. Okay. And if you see the previous waveform, see at this point I had stopped the gate pulses for T4 because no point having gate pulses beyond this point. But if you see at that point itself, T6 is getting triggered, T6. At this point, T6 is getting triggered. Okay. Now, T5 is connected to C phase, 6 is connected to B phase. See, the circuit configuration is something like this. C, B. 6 and 5. Now current can flow in this direction provided VCB is positive. VCB should be positive, only then you can have current in this way. Now let us see what happens. See here, VBC is negative. So at omega t is equal to pi by 3, VBC is negative, therefore VCB is positive. So VCB is positive, therefore, and current can flow. And what is that current? IC is equal to minus IB equal to VCB divided by 2R. Now VBC is Vm sin omega t minus 120 degrees. For CB I am adding 180 degrees because we have defined AB, BC and CA. So divided by 2R, and IA is equal to 0. And what is this value of current? This value of current you need to substitute omega t is equal to 60 degrees. Okay. So you will get the value of this current by substituting it here. That is the value of IC. Okay. So where does T5 stop conducting? Now at omega t is equal to 2 pi by 3, VBC becomes 0 or VCB becomes 0, and VBC becomes positive. In other words, VCB becomes negative. T5 has to turn off at this point. Okay. Because see in this direction, current to flow in this way, C should be at a higher potential than B. So that means VCB should be positive. Okay. So when it is 0, T5 turns off. Where does it become 0? At this point it becomes 0. So at that point IC or T5 turns off. So till here I have shown the gate pulses for T5. See this figure. See here. At this point I have shown the trigger pulses for 5. And that point T1 gets triggered. T1. Okay. 1 and 6 will conduct. 1 and 6. Voltage is VAB. See, I will show you. 1 and 6. 1 and 6. Same thing that we did for 4 and 5, 5 and 6, and 1 and 6. So at any given time only two thyristor are conducting, where alpha is equal to 90 degrees. Now we will see for alpha is equal to 30 degrees, what does it happen? Okay. So here are, for alpha is equal to 90 degrees, I have shown you the line voltages, gate pulses and currents. Only two phases carry current at a time. One phase is open. One phase is open. See, there is no current here. Now for alpha is equal to 30 degrees. Now I have shown here, in addition, I have shown you the phase voltages also. Phase voltages as well as the line to line voltages. alpha is equal to 30 is somewhere at this point. This alpha is equal to 30 degrees. That is T1, T2, T3, T4, T5, T6. Okay. Now, if you see in this figure, at omega t is equal to 0, T4 is getting a trigger pulse, T5 is getting a trigger pulse, T6 is getting a trigger pulse. Now, can they conduct? See, if you see the equivalent circuit, T4 is connected like this, T5 is connected in this fashion, T6 is connected in this fashion. Now, you can have a current flowing from T5 to T4 provided VCA is positive. VCA is positive. Yes, in this region VCA is positive. CA is positive. You can have current flowing from T5 to T6 provided VCB is positive. Okay. Yes, VBC is negative, so therefore VCB is positive. So therefore T4, T5, T6 can conduct because all the conditions are satisfied. They are getting trigger pulses, they are forward biased. Since all three phases are conducting, I need to use the rule which is used in three-phase circuits, that IA plus IB plus IC should be equal to 0. Okay. So IC is equal to minus of IA plus IB. And where does IA become 0? See here. IA becomes 0 at this point where VAN becomes 0. Where VAN becomes 0. At this point IA becomes 0. So when IA becomes 0, T4 turns off. So at omega t is equal to pi by 6, VAN becomes 0, therefore IA becomes 0, T4 turns off. Now T1 is getting triggered at this point. See, alpha is measured with respect to this point at 30 degrees. See, T1 is getting triggered at this point. So for some time for 30 degrees, only 5 and 6 are conducting. What is the condition for 5 and 6 to conduct? 5 is connected to C phase, 6 is connected to B phase. V, C, B should be positive. VCB should be positive. See here, this is VBC, so VBC is negative, therefore VCB is positive. So they can conduct. 5 and 6 can conduct at this point. Okay. Now the circuit equation is IC is equal to minus IB, okay, and current is VCB divided by 2R. So the current waveform is, see, in this region 0 to pi by 6, IA plus IB plus IC is equal to 0. See, IA is negative, IB is also negative, and IC is positive. Now from pi by 6 to pi by 3, IA is 0, and at that time IC is equal to minus of IB. Okay, this is the current. At omega t is equal to pi by 3, T1 is triggered. Now what happens? Now the circuit diagram is something like this. T1 is triggered. Now current can flow from T1 to T6 if VAB is positive. Yes, it is. VAB is positive. VAB is positive. Okay. See, at this is a line to line voltage. Reference point is alpha is equal to 0. Is this the point? Alpha is 30 is this. So this beyond VAB is positive. Now current to flow in this way, VCB also should be positive. Yes, see here, this is VBC, we are somewhere in this zone. Now VBC is negative, therefore VCB is positive. VBC is negative, therefore VCB is positive. So therefore it is possible. So current will starts flowing in this direction. Okay. So in this mode, three traces are conducting. What are they? T1, T5 and T6. Okay. This continues for another 30 degrees. At that time, after 30 degrees, T5 turns off. Why? When three terraces are conducting, I need to use the same rule. IA plus IB plus IC should be equal to 0. So if any one of the phase voltages become 0, at that time, the thyristor which is connected to that phase should turn off. Okay. See, I will show you the phase voltages. After 30 degrees, somewhere at this point, see, VCN is becoming 0. VCN is becoming 0. So T5 turns off. 5 turns off. So I have stopped, or this is the boundary for T5 gate pulses. So remember, if three thyrisors are conducting, I need to use IA plus IB plus IC is equal to 0. Load is resistive. So till the phase voltage becomes 0, the equivalent circuit which consists of three thyristors is valid. The moment the one of the phase voltages becomes 0, the thyristor which is connected to that phase turns off, and till the new thyristor is triggered, only two of them will be carrying current. Okay. And this principle you need to use to analyze three-phase AC voltage regulators. It is not very straightforward as compared to a three-phase AC to DC bridge rectifiers. That is the reason I told you this is not very straightforward, but then it is not very difficult either. Okay. Yeah, with that I conclude my lecture on power electronics. For the last 43 lectures or so, I have tried to give you just the overview of the power electronics. Subject is really vast. Okay. I encourage you people to take up a good textbook. Fortunately, a large number of very good textbooks are available, which was not the case during my undergraduate days. Not many books on power electronics were available, which is not the case now. A large number of very good books are available. Pick up a book, a good book on power electronics, and start reading it. Only then the efforts which I have taken will bear fruit. Thank you and good luck to all of you.